And I will pin this. Hopefully I will notice when we can see it and when we can't. All right, so there is not a whole lot to this particular section. It is complicated, but there's not a ton of it. It revolves around which means that in a right triangle, which also has an angle of theta, I guess degrees, but it could be measured in other things, that the sine of theta, and the SO of SOHCAHTOA, or the S of SO of SOHCAHTOA, stands for sine, is equal to the opposite over the hypotenuse. So opposite of that angle theta is A, and the hypotenuse we will call C. That the cosine of theta, the ka of SOHCAHTOA, tells me that cosine is adjacent leg over hypotenuse. So that would be B over C. Say B. No difference between the fractions written up and down and the ones written side by side. Tangent of theta, well, the TOA of SOHCAHTOA tells me that tangent is opposite over adjacent, equals A over C. So that really is the heart and soul. That is the stuff which is definitions, and we have to learn. The rest of it is just based on that. Like if I had another angle, we don't have to use Greek letters for them. We could use x. Then I would say that the sine of x is opposite of x, which is b over the hypotenuse c. The cosine of x is the adjacent leg to x, which is a over the hypotenuse c. And the tangent of x equals the opposite of x, which is b. I think I made a mistake over here. Over. B. Let's go. I'm gonna pause this recording. Noting that the three angles in any triangle add up to 180. So since there's 90 there, those two have to add up to 90. Therefore, they are complementary. This is true of any two complementary angles, that the sine of one will equal the cosine of the other. Okay, so that is the basic gist. We have done things with that. Like, for example, we have put it together with our 30, 60, 90 triangles to discover what the sine of 30 is every single time. And I don't care which triangle you're looking at here. You can fill in your favorite number here, which I will put as F for your favorite number. Well, this will be 2F. Maybe F was 10 and 2F is 20. So we'd get 10 over 20, which reduces to 1 over 2. Maybe your favorite number is F. That's okay. Variables are good numbers. F over 2F, the F's cancel out. I'm left with 1 over 2. Regardless, the sine of 30 is always 1 over 2. We can do the same thing for cosine, tangent. We could do the same thing with 45, 45, 90 triangles, and so on. That was all of section 9.8. In 9.9, we got to look at this handy dandy chart. 9.9, handy dandy chart, which works in two ways. So I like the presumably wrong story, but I like the presumably wrong story that there were 90 people who all of whom drew a triangle with a slightly different right triangle with a slightly different other angle. And they measured those sides very, very accurately. And they found the ratio of the opposite to the hypotenuse, the adjacent to the hypotenuse, and the opposite to the adjacent, and listed them here for us. I like that story. It gives you like real tangible idea of how this chart came into being. And from this chart, we can now do problems like the kind of basic, everyone can understand it, even though it might not seem all too useful problem of finding the height of a tree or a flagpole or something like that. So if this is a flagpole and this is level ground, and it's pretty easy to measure an angle here, let's make it 27 degrees. And it's pretty easy to measure this length. Let's make it 100. Then I could say, oh, well, I'm interested in the height of my flagpole and the trigonometric ratio, which relates one to the other. I'm looking for the opposite. I know the adjacent. That would be tangent of 27 equals x over 100. I can look at my chart, look at 27, look at tangent, and well, it makes it pretty easy. It's about 0.51. And so replace this with 0.51 equals x over 100. And so 51 in whatever these were, feet, meters, miles, who knows, equals that x. It'd be pretty awkward if that were in miles. That is one of the two uses for this. The other use is going backwards. So now that we have this handy dandy chart and all these ratios of sides listed, well, what if I was out there and I discovered a triangle, a right triangle, and I found that this had a length of 1 and this had a length of 10. I could figure out what this is with Pythagoras, but I'm more interested in what this angle is. So I could call it x, I could call it theta, I could call it whatever variable I want. People seem to like x's. I could say, oh, I know the opposite and the hypotenuse. So the sine of x will always end up taking the sine, cosine, or tangent of an angle. And when you do so, you get a ratio of sides is 1/10. Of course, I picked those numbers because I can convert that easily into a decimal. So sine of x is equal to 0.1. So now I can look at my chart and use it the other way, where I'm looking to see, okay, somewhere in there, where I'm looking to see what angle is associated with that ratio of sides being 0.1. So it seems to be somewhere between 5 degrees and 6 degrees, a lot closer to 6 degrees. I think it is fair to say that x is equal to 6 degrees. Pretty clear? I got a nod. I got a overabundance of people who I can't see, one of whom gave me a thumbs up. Thank you. Other people who I can see, thumbs up, thumbs down, thumbs somewhere in between. That thumbs up. Awesome, awesome, awesome. So that, of course, was just a recap. There was no new information there. Let's jump in. I'm going to pause this because it won't be. All right. So in problem number 15, given a trapezoid with sides 5, 10, 17, and 10, notice that it had 2 congruent sides. If a trapezoid has 2 congruent sides, it is isosceles. If they were the top and the bottom, which were congruent, which are also parallel, then you'd have yourself a parallelogram instead. And then all the sides, opposite sides, would be congruent. So we definitely don't have that. So here is 10, 10. Here is 5. I'm probably not ever going to write 17. Well, I could. I'll write 17. I guess I was wrong. We'll write 17. That whole thing is 17. Well, I split this thing into a rectangle, so that's got to be 5. And I'm subtracting 5. I've got 12, meaning 6 of it goes here and 6 of it goes there.
Okay.
And now I see a 6 blank 10 triangle without doing any work, without bugging Pythagoras. I would expect you guys to be able to put in 8. Okay, what is the question actually asking? Find the sine of one of the acute angles. So here is one of my acute angles. Sine is opposite over hypotenuse. So the sine of this angle, I'll call it A for acute, sine of angle A is 8 over 10, which of course reduces to 4 over 5. And that would be my answer.
Yeah, I set this up totally wrong then, because I didn't. Did it say isosceles triangle? Trapezoid?
It did not say isosceles trapezoid, but it gave me those two sides as 10 and 10.
Oh,
So it's got to be the two legs which are congruent.
right.
Especially this book would never call something where the bases are congruent and parallel a trapezoid.
Can we also go over number 13 on page uh 425?
Yeah, of course. Number 13 on 425. Find the perimeter of a trapezoid. Okay, we seem to not love these trapezoids. Where, okay, A, B, C, D. Where A, B is one of the A, B, C, D. The first time I tried to draw this, instead of drawing A, B, C, D, I drew A, B, D, C, and then tried to follow this around, and boy, it did not work out well for me. This is 13. They tell me that AD is 2, that DC is also 2, despite the way I drew it, and that CB is 2. They tell me that the cosine of angle A is 1/2, which would be enough information, even without my chart, for me to know that that is a 60-degree angle, but you don't even have to recognize that. A cosine is the ratio of the adjacent side, which I put a little x on, to the hypotenuse. So cosine of A equals 1 over 2 equals x over 2. And without breaking a sweat, we can realize that x has to equal 1. Again, we have one of these isosceles trapezoids. So the same thing on the other side. This is 1. This is x equals 1. And on the bottom of my rectangle has to be the same as the top of my rectangle. There's a 2. So to find the perimeter, 2 plus 2 plus 2 plus 1 plus 2 plus 1. I believe that that perimeter should equal 10.
So why can't the adjacent be the height then?
The adjacent be this height, like here,
Yeah.
because that is opposite that angle. It is not one of the sides which forms that angle. It is literally across from that angle. So,
Oh, we're finding that angle. Oh.
yes,
Oh,
this
I
is,
was looking at the right angle. I was looking at the right angle. So that's why.
yes, we do not, this year, we won't find the sine, the cosine, or the tangent of right angles. Although next year you will, or not next year, but in 2 years you will. Yeah, again, can we use the chart on the test? Absolutely. I will provide you with a partial chart. It'll have everything you need, but it might not have everything you want. Maybe you're looking up what the cosine of 60 degrees is. I'm not going to tell you. I'll just tell you that right now, that I'm not going to give you the sine, the cosine, the tangent of 45, 30, or 60, because you should be able to find that on your own. And maybe you're looking up what the sine of 20 is and it's not there, but the cosine of 70 is. Those two things are the same. Any other questions before we jump back into practice? Nope, nope.